Dr. Paul Allaire, retired UVA chaired professor and chief technical officer of Rotor Bearing Solutions International, and now part-time professor at Wake Forest University in the engineering department. Paul, I want to welcome you to SciTech. You are actually roughly our 75th speaker in this over 10 years series that we've had. And I just want to welcome you today and very excited about your lecture. This is a really interesting area, and you've done some incredible work within mechanical engineering using your knowledge to better human health using artificial hearts. Could you tell us a little bit about yourself, please?
I'm a mechanical engineer and have taught at universities for a very long time and enjoyed almost every minute of it. And I'd like to present this talk about artificial heart pumps, which is by far the hardest thing I ever did, technically speaking.
Paul, take it away. Thank you.
Okay, so this talk is going to be have several parts, some of which show you how does a heart work, and then we'll go into what happens when the heart doesn't work properly and you have maybe a heart transplant, and then since there aren't enough transplant hearts to go around, then people have developed mechanical hearts. And we're going to talk about a couple of different kinds of mechanical hearts. Next slide, please. So this is the human heart, and basically it has a left side and a right side, and you can see the names on here. And so this is the most critical part of our body. If your heart doesn't work, you don't work. Next slide, please. So the heart has really 4 different chambers, but they're grouped together. So there's 2 chambers on each side of the heart. And we have a valve which allows the blood to keep going in the right direction. Next slide, please. As I mentioned, the heart is the most important muscle in the body. And so it's really a pump, or actually 2 pumps in one. The right side receives blood from the body and then pumps it to the lungs. And the left side does the opposite. It receives the blood from the lungs with oxygen in it, and then pumps it around to the body and keeps you alive. Next slide, please. So the heart is an involuntary muscle. And what that means is that it beats, and you don't have to use your head to tell it to beat. It beats whether you tell it or not. The human heart averages 100,000 beats daily, which is amazing. And then each beat fills your heart with blood, and then it contracts to pump the blood through the body. Next slide, please. This shows sort of a blood circuit diagram going through the body, and I won't spend any time with that. It's rather complicated, but it shows that these are all your veins and other parts of your human blood flow system. Next slide, please. So your heart is about the same size as your fist, and it averages 70 beats per minute. And that adds up to, if you live to be 80 years old, that's 30 billion beats with a B. And so it's amazing. An adult heart pumps about 7,500 liters per minute, per day, excuse me. Next slide, please. So this is part 2 of the talk. And when one, the left or right ventricle loses the ability to keep up with the amount of blood it needs, then it fails. It could be the left side or right side. Usually with people, it's the left side first. And about 5 million Americans live with heart failure, and about 500,000 new cases are diagnosed every year. Next slide, please. Okay, so when you do work on hearts, you have to get some sort of what I call a blood and guts slide like this. This is a heart which is being transplanted, and it's shown in the heart surgeon's hand. And you can see that it's kind of a difficult business to take one out of one person and put it into another. Next slide, please. This is a summary showing some information about heart transplants. First one was in the 1960s. Then about 20 years later, anti-rejection medications became available. Now, anti-rejection is necessary because when you put in a different person's heart, your body thinks, oh, this is something I need to reject. And so your body would actually attack the new heart. So you have to put in medications to prevent that. And so far, we don't have enough donor hearts, so we can't get enough heart transplants. Next slide, please. And this shows the survival rate with number of years. And as the number of years go along with your new transplanted heart, various medical issues come up. And so, but generally, the heart lifetime is something like 20 years. Okay, so here's the left-sided heart failure, which involves the left ventricle. And there's a number of things listed here which happen to your heart. And I'll leave it to the reader of the lecture slides to look at this list here. Next slide, please. This is part 3 concerning the need for artificial heart pumps. As I mentioned before, there's only about 2,500 donors available in need for each year. And by the way, here's a commercial. You need to check off on your driver's license that you'll be a donor. Please, everybody do that. So one solution is to make an artificial heart pump. And so in the diagram that you can see here, you see that there's a heart, but there's an additional pump installed just below that heart. And you can see we have to punch a hole in the left ventricle of the heart and then put in a pipe, small pipe, or cannula it's called. Then there's what's called an axial flow pump there, and then we pump the blood back up into the top part of the heart. And then, so what you see is we have two hearts. You have the native heart, which is still beating, but not pumping enough. And then we add a mechanical heart in addition to pump more so that you get the blood flow rate up to where it should be. The first one of these was done in 1969. Here is a very complex mechanical heart or artificial heart that has both left and right side units, and it pumps back and forth. It's a pumping heart, and you can see where it goes into the heart in the thoracic unit there. And you also have to have a power supply, an external battery pack, and then you transfer the energy through the skin through a wireless energy transfer system. And then there's a small computer, which is an internal controller unit, and these are connected to the heart, and the heart beats, and you can see it right there. In this particular case, the native heart has been removed, so you have no native heart. Next slide, please. So this is a history of artificial hearts. In 1969, one was put in by Dr. Leota, and this was the first implanted into a human as a bridge to transplant. The patient survived 3 days on the artificial heart, and then a implanted heart was put into the person, and they lived for quite a while after that. In 1982, Doctors Wilhelm Kloff and Donald Ostone and Robert Jarvik designed a new artificial heart, which would be put in as a long-term artificial heart, but it was somewhat successful. And let's go to the next slide, please. So this was the first patient, Barney Clark, in 1982 at the University of Utah Cardiovascular Center. And the Jarvik 7 was implanted into him, and he lasted for 112 days duration. He was kept alive. He would otherwise have died right away. but he had to be attached to a 400-pound compressor, which is not exactly portable. So we had to miniaturize and do lots of other things to make this heart better. The next slide shows a lot of different artificial heart pumps. There have been many developed, and I'm not going to go through all of these, but you can see there's an Arrow Lion heart. This is a centrifugal pump, Micromed DeBakey, and all these different pumps that have been developed. Many of them have been improved and have gotten a lot better. Next slide, please. This shows an axial ventricular assist device that it sort of looks like a pencil-shaped thing. Here's one called the Jarvik 2000 and the Micromed DeBakey on the right-hand side, and Heartmate 2, which is widely used around the world today, and some others. Next slide, please. So this is left ventricular assist devices survival rates, and this plots the percent survival versus months post-implant, and you can see that the survival rate after about 4 years is about 50%. So it's not perfect, and there's still quite a few issues that need to be resolved. The next slide shows two pumps. Example, left ventricular assist devices. The left one is an axial flow pump, and it's called the Heartmate 2, and it's the most used in the world right now. And then on the right-hand side is a centrifugal pump, which is a circular kind of thing, which is a small blood pump, and you can see the flow coming in and going out. Next slide, please. This is the most widely used VAD. It's called the Thoratec Heartmate 2 LVAD. Approximately 27,000 have been put into people so far. The first device was put in 2001, and it's a rotating continuous flow pump driven by a small electric motor operating at about 6,000 to 15,000 RPM. The medical team sets the operating speed. So it puts out about 2.5 to 10 liters per minute, and it has to come up with 100 millimeters of mercury pressure so that pushes the blood through the veins and arteries. Now, this is a rotating pump, so it has no pulse. However, it's used in parallel with the existing heart. So the pulse that you have comes from the native heart, which is still in existence. Cost is about $75,000 to $85,000. That's just for the pump. That doesn't include the surgery. And there are some blood lubricated bearings, and the length of it is about 3 inches. Next slide, please. So one of the problems with the pump that we just talked about is that it has rotating bearings which are lubricated with the blood, and these create a lot of blood clots. And as you know, if a blood clot starts in your heart and goes to your brain, that's called a stroke, and you don't do very well if you get a stroke. So a motivation has occurred, and this whole heart pump industry is changing and going to magnetic bearing supported devices, because then you don't need blood bearings. You can support the rotating part of your pump with a magnetic field. Think of like magnets that support something. Next slide, please. So this is what I mentioned a few minutes ago. The blood immersed needle bearings at each end of the impeller create thrombus, which is what the medical people call a blood clot. And so there are a reasonably high rate of failures due to this blood clotting. Next slide, please. So I was contacted by the University of Utah heart pump program and asked if I could develop or actually myself and my team, developed a magnetic bearing supported pump which would not have any blood clotting problems. So we started designing this, and as it turns out, magnetic bearings were invented across the street from my office in the physics building at the University of Virginia. So I knew about magnetic bearings quite a bit. Now, as I mentioned, I knew magnetic bearings pretty well, but I had to learn a huge amount about heart pumps and circulatory systems and what were all the things you had to do. So as I mentioned before, this is the hardest thing I ever did in my technical life. So we developed the world's first magnetic bearing heart pump at about 1995. And you can see the pictures here. There's a small electric motor which drives the rotating pump. And you can see the diagrams with the magnetic bearings in there, which supported the rotating impeller without any blood bearings. And we had no thrombus or hemolysis, which is additional blood damage. It weighed about 1 kilogram, and it had a titanium impeller. You use titanium because the blood doesn't react with titanium, it accepts titanium. Next slide, please. So here's a picture of the world's first magnetic bearing supported artificial heart, or LVAD. And you can see the impeller in this person's hand. And you can see the housing behind it with the magnetic bearings installed, and then the top on the left. And so that's the size of it. And so this was designed and built, and then of course we had to test it. There's a small computer which operates it, which goes outside of the body, and then you have to have wires going through the skin, just like all the other pumps. Next slide, please. So this is testing. Now we have a pump, and the National Institute of Health requires that you try out your pump in an animal first. And so this is a calf. And so our pump was put into a calf, and the calf was standing there covered with the surgical sheets. And then here's Dr. Olson of our group, who is implanting this artificial heart into a calf. And what we found out in the first one that we built was that the coils heated up too much. And so the heart was actually getting hot. And as you probably know, you can't heat up blood too much or you do blood damage. So if you think about this as a student and you're testing something in the laboratory, so what do? So Dr. Olson called me up and said, what do we do about this? And I said, well, the only thing you can do is put ice on it, as far as I can tell. So they had to put a bag of ice on top of the artificial heart inside the cow and change that every 4 hours. And National Institute of Health requires that the pump has to work for 90 days without being turned off. And so this one did that. And so this was regarded as a proof of concept. From an engineering point of view, we proved that it worked. And so after that, we got a large National Institute of Health grant, and then we redesigned it and changed some of the systems so that it wouldn't overheat. So this is our team and our funding. So it was University of Utah cardiovascular team, and then a UVA engineering team. And we went through, and I won't read through this long list, but we had to build another one. We got patents on our device and so on and so forth. And so eventually, this heart was, the rights to manufacture this heart were bought by World Heart, which is a company. And so the pump was developed further and then went into implants in Europe and Asia. And so the pump went on for about 7 years. And then finally, we weren't making it. The company wasn't making enough money, so they ended this particular program in 2011. But I was very happy because it worked. Okay, so then we worked on a second heart pump. This is the next heart pump, and I'm not going to spend too much time with this. But the surgeon said they didn't like the centrifugal heart pump because the center part stuck up too far. They wanted something that looked more like a pencil. And so we next developed the Lifeflow heart pump, as shown in this slide. Next slide, please. The next slide shows teams and funding too. There was quite a few things that we could improve with the initial Levacor, and we went through and got another large grant and developed another pump. However, at the end of that, no company picked up the manufacturing, and so that was the end of the project in about 2009. Next slide, please. So this was an axial flow pump. You can see the impeller, which rotates around. The flow goes in and comes out, and you can see the impeller had veins on it to do the pumping on the bottom right side. And this provided a very efficient, streamlined blood flow path. Next slide, please. So we also had to do animal fit trials. So we built just a metal version of the pump and installed it in a calf. And I'm sorry, this one was in a 70 kilogram adult sheep, but their anatomy is very similar to that of a calf. So just think if you were a student working on this project, that might be you putting it into this sheep. Next slide, please. This shows a cutaway version showing the impeller with the blades on it, and then the coils for the magnetic bearings. Next slide, please. This shows again, this shows a cutaway version of the vanes on the impeller. Next slide, please. And so one of the objectives of this research was to have a very smooth flow going through and avoid any recirculation regions or other problems. And we ended up with a very optimized flow path design. Next slide, please. In order to do this calculation and do the design, we use something called computational fluid dynamics, which is something widely used in engineering to do analysis and make sure that the flow is going to be good going through the pump. Next slide, please. And this shows a CFD analysis, and you can see some of the flow going through shown coming out of this. Next slide, please. And this shows the pump performance in terms of pressure rise versus the operating speed. And since we need about 100 millimeters of mercury, we can look at the yellow line. So the rotating speed of this pump would be set at 6,500 RPM. Next slide, please. This shows one of the flow patterns that wasn't proper, so we had to change the design, change the blade design so that it would be improved. Next slide, please. And then this shows the magnetic bearing parts of it. And this was very different from the first unit that we developed. And I won't go through the details. Somebody can contact me if they want more details about how this magnetic suspension worked. Next slide, please. And the predicted performance was that the magnetic suspension would take up only 1 to 2 watts. And then we also had to figure out, you might fall down when you have this pump installed in you. So the magnetic bearings can take shock loading. And so it'll keep working even if the person that has this device in them falls down. Next slide, please. Here's a picture of the magnetic bearings that were used in the pump. Next slide, please. And then this is the initial prototype testing. So this we were doing prior to it going into a calf for testing. Next slide, please. And so this is our pump testing prototype, or fluid test rig, we called it. And we made a pump out of plastic. So we got 3D printing to make a plastic pump, and we put it in, and we ran this with a little motor and measured the flow rate going through it. Next slide, please. This shows a photograph of a plastic pump impeller, and then we put it in a clear plastic housing, and then we used a laser to go through and measure the velocities in the fluid going through. And we found out that there was only about a 10% difference between the calculated values and the actual values that went through the testing. This was quite successful. Next slide, please. This is a different type of pump. So new pumps are coming along all of the time. And this is what is called a SynCardia Biventricular Total Artificial Heart. So this has both the left side and the right side as seen in the picture. And so you remove the native heart, which is failing or almost failing. And so this was approved in 2004, and there have been 1,700 implants to date. Next slide, please. So this is some new technology using magnetic bearings, and so we'll talk about that next. This is from a company. Okay, so this is the new device. This shows a picture of the new device of a total artificial heart from the University of Texas. And so obviously it has two sets of flows going in from the left side and the right side. Next slide, please. And this is a picture of it, the Bivacor total artificial heart. And you can see that it's a pretty small unit. The weight is 512 grams and the outer diameter 60 millimeters. And so this is a total artificial heart. So you have to provide a pulsatile blood flow. Remember that the left ventricular device, which rotates, did not produce any pulse, but the native heart that it was still coupled with produced a pulse. In this device, what they have to do is take the impellers, that is the pumping parts, and they have to slow it down and start it again fast in order to produce a pulsatile flow so that you'll have a heartbeat. Nobody knows if you can live without a heartbeat so far. So this one has to stop and start. And a big question is that going to create wear inside the pump and create other problems? So long-term testing has to be carried out and is being done so right now. Next slide, please. This is an expanded view of this Bivacor total artificial heart. And you can see it has a rotating impeller and then a bottom part and an upper part that has the magnetic bearings in there. Next slide, please. So what have we learned? There have been lots of progress in the last 50 years, and the movement is away from bulky pulsatile devices with lots of problems. And what has been happening is move to relatively high-speed, small, low-power rating pumps, and new advances in blood flow and combined motors, bearing cannulas, and so on. And so this is a very good thing, and so we're continuing to work on this. I personally would like a new other LVAD project, but that hasn't happened lately. So there's lots of funding out there if we go after it the right way. And we need a leading medical team, engineering team, proposal writers, and so on in order to get a new grant. So I'm interested in working on another one. I don't have one at the moment, though. Next slide. Thank you very much, and I hope you enjoyed the talk. You have my email contact on here, and you also have my mobile cell phone if you have any questions to ask me. Thank you very much.
This is a wonderful talk. I want to thank you on behalf of Foresight Tech, and thank you on behalf of our SciTech crew. And I do want to mention that there is a team behind this, and you've met Sean today, but also a fellow named John Reese, and also Dr. Dwayne Davis, who's helped me with this particular SciTech lecture series for the last 10 years. Would you take a question or two?
Sure.
Okay, great. Paul, this is fascinating. I remember as a young man, might have been 18 at the time when the first heart transplant was done, and it was just astounding because I think it shocked people. And here we are 50 years later, and it seems like there are pumps that have been improved, come and gone. And then, your technology, this idea of using magnetic forces to drive the pumps, is this the state of the art right now?
Yes. Well, we have a saying in my group, magnetic bearings are attractive.
Right. The question I have for you now is, we have a grant, actually I have a grant under my purview called Beta Skills, which is biomedical emerging technology applications. And this one would actually fit just beautifully with respect to what we're thinking. Do you envision us, the Institute for Regenerative Medicine is down the street from us at Wake Forest. Do you envision in, I don't know, the next decade or two, the possibility of regrowing somebody's heart using their own cells?
That's certainly a possibility. I don't know enough about that topic to give you a detailed answer.
Great. Have you had a chance to meet with the folks at the Institute?
I have not. I didn't even know we had one.
Well, I'm going to make that connection for you, because I think that they would love to know that you're in town, and okay. I think you would have a great. My last question for you is, there's so much engineering here, there's so much health here, there's so much biology here. At our place, we train technicians, and we educate technicians. And of course, there are a lot of people that go on to take their bachelor's, their master's, and their PhDs and so forth. But there are jobs, and we have a lot of heart-related technology, sonography being an example. From a biomedical engineering perspective, when you were doing this, did you have technicians helping you, and do you see the technician workforce as being a priority going forward because of these advancements in biomedical devices?
Okay, that's several questions. Let me answer the first part. We did not have technicians in my laboratory. We had undergraduate and graduate students who did all the design work and whatnot. And then companies built the components for us. They did the machining and constructing the various parts. We put it together and tested it in our lab. However, when it went to World Heart and they started manufacturing this for implants into bodies, then they used a lot of technicians for that.
Excellent. And yeah, I did ask you a lot of questions, and it was a mouthful.
Okay.
So I know that you've offered to come over to the college when COVID passes us by, and so I'd just like to invite you to come and see us, and maybe you can meet some of those prospective technicians and also the engineering people that are actually going through their education, and that'll, we'll see when that happens, because right now things are tight because of COVID. But
Yes.
Paul, I want to thank you very much. It's been a pleasure. We've been planning this for several months now, and I'm very happy we were able to get it together. I want to thank Sean too for today's recording.
Yes. Well, thank you very much for setting all this up. And so now, at least I can say I've done one thing on Teams and been successful.
Very good.
A lot of help from you guys.
Thank you.
Well, I
Sean,
appreciate you being willing to do this, and I don't know, I've been in education for a very long time, and this is part of education where you do things like this for people to, give them some nice talks that they can hopefully enjoy.
Absolutely. Thank you. Sean, do you have any questions?
No, I'm all set.
Oh, the only thing that I forgot when I got into the middle of this talk here was that I usually look out at all the students and I ask if I have any volunteers who want to try one of these.
And what's the reaction?
Haven't gotten one yet.
I can understand why. Mind you, I would tell you something that personally, if I was having a heart disease and I didn't have much of a hope, I would love to have tried one. Hopefully by the time that I might have to try one, that will be pretty far along with respect to these. But you've done admirable work, Paul. Congratulations.
Oh, thank you. I was another story that I forget. I forgot in the middle of this one was, okay, so this doctor walks up to me. I was at this magnetic bearing conference, and this doctor walks up to me, and the one I ended up working with, and says, "How would you like to put magnetic bearings in an artificial heart?" My response is, "What's an artificial heart?" I didn't know,
Yeah, of course.
Anyway, so that's where I started.
Very good. Well, Paul, I want to wish you a happy day today.
All right.
I hope the renovations have gone well.
They have, yeah. We're in pretty good shape now. The house is in good shape.
Excellent. Good. Well, I look forward to meeting you in person when things are right.
Yes. Thank you.